Hey everyone, so this is problem 3.1 out of Griffiths' Introduction to Quantum Mechanics. Before I get into solving this problem, if you wouldn't mind liking this video and subscribing to my channel, it'd really help me out. It's a great free way to support me, and I post a lot of solutions from undergraduate textbooks, so I think you have a lot to gain from this. Now let's get into actually solving this problem. It says, show that the set of all square integrable functions is a vector space. The main point is to show that the sum of two square integrable functions is itself square integrable. Use equation 3.7. Is the set of all normalized vector functions a vector space? So a vector space is defined by a few properties, one of which is closure. So what closure says is if you have two vectors in the vector space, let's say alpha comma beta is an element of the vector space, they add to another vector, gamma, which is also an element of that vector space. Okay, there's a few other properties. For example, there has to be a vector 0. There has to be an identity. There has to be associative, commutative, stuff like that. But to focus on what it wants us to show, what we want to show is that if you take two square integral functions, that gives you another square integral function. So let's just take fx, gx, and just your definition for something to be square integrable. The integral over some interval of the modulus squared has to be less than infinity. This is equation 3.4. And we're going to say f of x and g of x both satisfy that condition. Okay? And what we want to show is that f of x plus g of x, that's also satisfied. So first I'm going to show you a helpful identity. The modulus of x plus y squared. I'm just going to use x plus y, but you can imagine this is f and g. That's the same thing as x plus y and then our times x plus y, which if you distribute is x dot x plus x dot y plus y dot x plus y dot y, which is x dot x plus 2 x dot y plus y dot y. This might look a little funny, but I promise this will be relevant for what we do. Additionally, we could do something very similar with x minus y. And you're going to get x minus y, x minus y. And you're going to get x dot x plus minus 2 x dot y plus y dot y. So if you do this plus this, if we were to add the two, clearly these terms are 0. So we'll have 2 mod x squared because that's what that is, and these add, plus 2 mod y squared, because that's what the y dot y is, and of course we're going to add them. Okay? So we have this property is going to be useful here. So what we can say then is that f of x plus g of x squared, that is going to be less than or equal to mod f of x squared plus 2 mod g of x squared. Why can we say that? Well, we know that this number here is just some positive value, right? Because of the absolute value, that's going to be some positive quantity. So if we were to subtract that off, the left-hand side of this equation here, the left-hand side is getting smaller, because really we just have this part, right? That's all that is. So since we're taking away that circle term, it must be less than or equal to the right-hand side, because again, that circle side is positive because of the absolute value. So if we take it away, we're going to get this sort of triangle inequality. I hope that makes sense. And the reason why that's helpful is now we can integrate both sides. And we're going to get this inequality. The 2 I can factor outside of the integral. That's not an issue. Never an issue to do that. And as I'm writing this out, since it's so mindless, I hope what I explained was clear on why it's less than. I think it's clear, but obviously I've done this, so from the outside maybe it's not. Now why is this useful? Well, again, we know f of x and gf is square integrable, which means this is going to be less than infinity, right? That's just the definition. But g of x is 2, so that's going to be less than, well, I have it backwards, don't I? A little silly of me. That's less than, no wait, I had it right. You get what I'm saying. This whole term is less than infinity, and this whole term is less than infinity. So 2 terms that are less than infinity multiplied by 2 and added together, well, that's still less than infinity. So this whole side has to be strictly less than infinity, right? So then f of x plus g of x is also square integrable because it satisfies that condition. I hope that makes sense. Okay. Next up, we want to look at the set of all normalized functions, which is, that condition's a little different. It's actually a little more strict and restricting, because it says that this quantity we are interested in is equal to 1. So it can't just be less than infinity. It has to be 1 as well. And the question is that a vector space? And again, you have a list of different conditions you could go through and see if any of them fail. And if any one of those conditions fail, then it's not a vector space. So one condition is that the 0 vector has to be an element of your vector space. And the 0 vector will just be 0 times any vector, where v It's an element of the vector space, returns the null vector, or 0. Well, that's a little bit of a problem here, because if we take f of x equals 0, clearly that integral is not equal to 1. So the null vector that we need to be an element of our vector space is not included. It doesn't satisfy that condition and is not a part of the set of normal. It's not an element of the set of all normalized functions. And because it fails that one condition, we know that this is not a vector space. If it failed any condition, if you were to find another condition for a vector space that failed, then it's not a vector space. I think that's the easiest one to show. That's the one that came to my mind first. So that's what I did. Part B says, show that the integral in equation 3.6 satisfies the condition for an interproduct. So for part B, the way that we defined an interproduct is as followed. It's the integral from a to b, f of x complex conjugate, g of x dx. This is equation 3.6 in your textbook. Okay, so condition 1. So the first condition we want to show is that if you have the inner product between two vectors like this, you can express it in this form. This is in the textbook as well, but this is the first condition. So let's see if that works. We know this by the definition. Since G is the bra, that is your complex conjugate part. And now if we were to take the complex conjugate of all this, that'll be equal to the integral from a to b. Now our function f is complex conjugated, and g of x no longer is, because we're taking the complex conjugate of the complex conjugate. And then this is clearly equal to, so I should have mentioned, that's equal to this inner product. So that condition is satisfied. That's the first one we looked at. There's another condition which says that the inner product between two identical vectors is greater than or equal to 0, and it's 0 if and only if your vector A is the null vector. Okay, so let's take the inner product of two identical vectors. Okay, that's what 3.6 tells us to do. And this is, of course, just the integral of the modulus squared of f of x. Okay. But we know that modulus f of x squared must be greater than or equal to 0. Okay. So since that's greater than or equal to 0, we're going to be finding the area over some positive function, which means this whole thing is in fact positive. And of course, if it is 0, then the integral of 0 is 0. So that takes care of the if and only if part. One last condition to make sure everything checks out. It's pretty straightforward. We just want to show that if you have this sort of, in other words, you have this bra alpha, then you have B, some constant, C, some constant, acting on these kets, beta and gamma. And essentially we just want to show that that is going to be equal to B times the inner product here, plus C times this other interproduct. In other words, our alpha distributes as we expect, and the constants can be factored out. So let's plug this into the integral, actually. We'll have integral from A to B. Alpha is complex conjugated. We have B, beta, d of x, plus, so that's this first term here. The second term, again, and of course we can factor constants out of the integral. That's why this makes sense. And these are the definitions of our interproduct, right? So the reason why this really works, why we have this sort of linear property, it's because the integral is linear. So the fact that this property holds really shouldn't be surprising. Okay, so that's how I did problem 3.1. I hope that helps you, and if it did help you, please leave a like and subscribe. Thank you.